In section 11.3, we're going to be looking at two means, but these are going to come from independent samples. They will not be from matched pairs, okay? It will not be comparing who won the presidential election to the loser. It will not be comparing their heights. It will not be comparing the same person, but their response from red to blue. So if they're not matched, it's just two generic different groups. They are not matched together, okay? So we will still have some standard notations. Mu1 means the mean from population number 1, and mu2 will be the mean for population number 2. So it could be men and women. It could be, people in one town compared to people in another town, their means or their averages, but they will not be matched. It will not be, father to son or a husband to wife or one twin A to twin B. It will not be matched, okay? N is still our sample size from group 1 or group 2. X bar will be your sample mean from group 1 or group 2. And then S will be the standard deviation from group 1 or group 2. Okay? Your hypothesis, if you are doing, looking back at our chart here, we're doing means. We have two groups, so two means, and as opposed to just one, two means, but they're independent samples. In other words, not matched pairs, independent samples. Your null hypothesis has to be that the mean from population 1 equals the mean from population 2. That has to be your null hypothesis. Okay? Your alternative hypothesis, your claim, your H1, will be that those means are not equal, or that mean 1 was greater, or that mean 1 was less than, whichever one applies. Okay? Your notes remind you, or your formula chart will remind you, that when you're doing two means from independent samples, you will pick two sample t-test if you're doing hypothesis test, and you will pick two sample t-int if you're doing confidence intervals. Okay? Remember when we did just one sample, we picked t-int. So we're still doing t's, t-int or t-test, but we're picking the two sample in front because you're going to have two different groups. When you get ready to type it in your calculator, it's going to ask you if you want it to be pooled or not. We will say no, okay? There are times when you would want it pooled, obviously. That's why it's giving you that choice. But for our class, for what we're doing, the answer will be no. The default is no, so just leave it alone. Don't change that setting when you get to that in your calculator. All right, let's look at an example here. For a sample of 1,657 men, ages 65 to 74, the mean weight is 164 pounds and the standard deviation is 27 pounds. For a sample of 804 men aged 25 to 34, the mean weight is 176 pounds and the standard deviation is 35 pounds. Okay? So notice we have two different age groups. We have some older men aged 65 to 74 and we have some younger men aged 25 to 34. That's how I'm going to split my groups up. I'm going to call them the older and the younger. One of these groups is going to be my group 1 and the other one's going to be group 2. It does not matter which you pick. I'm just going to put the older as group 1 because they mentioned them first, but it really doesn't matter. And the younger I'm going to let be my group 2. Okay? For the older men, the mean weight, that average weight, so the X bar, is 164. The standard deviation is 27, so S is 27. I'm going to put 1s by each of these as my symbol that they were in group 1. And it said there was a sample size of 1,657. So N1 is 1657. Okay. Younger, I had 804 men. That was my sample size. So N2 is 804. The mean weight, so X bar for group 2 was 176. And the standard deviation was 35. Okay. I would point out, notice that the sample sizes are different. That's another good clue. Since your sample sizes are different, that's another good clue that there's no way it's matched pairs. If it's matched pairs, each person in one group has to be matched directly to someone in the other, and that can't happen if they're different sample sizes. All right, they want us to test the claim that the older men have a lower mean weight than the younger. So in other words, they want to claim that the older weight, the older mu from group 1, the mean, not just from the sample, because X bar is our sample mean. Mu would be our population mean. So they want us to see if the mu, the mean from the older population, is less or lower than the mean from group 2. Okay? That's our claim. That's what they want us to test. Okay? Remember, your formula chart tells you exactly what your null hypothesis should be. So for two means, when we have independent samples, our null hypothesis has to be that mu1 equals mu2. Our claim, what we believe, is that mu1 is less than mu2. Okay? Remember, we always have to put mu1 first. That always has to be our first number here. Our level of significance was 0.01. And now I'm going to feed this into my calculator. So I'm going to go to Stat, Test, and they are telling us, remember, to pick 2 sample t-tests. So I'm going to arrow down to 2 sample t-tests. Make sure you don't accidentally pick 2 sample z-test. So 2 sample t-test. We have data, not statistics. We have statistics. We don't have the data. Sorry about that. We have statistics. And then it's asking us for these values. So X bar 1 was 164. X bar 1 was 164. Standard deviation from group 1 was 27. And the number in group 1 was 1657. X bar for group 2 was 176, standard deviation was 35, and our sample size was 804. Our symbol in our alternative hypothesis was less than. That's why mu1 always has to be first. It's saying mu1 is what to mu2? Is it not equal to mu2? Is it less than mu2? Is it greater than mu2? Ours is less than. And leave it on no for pooled. And then tell it to calculate. It will give you your test statistic. Our test statistic is negative 8.56. It will give you your p-value. Our p-value is 0. I don't know that I've ever seen a p-value of exactly 0, but it is. And now we make our decision. Remember, we compare p to alpha. P is 0. Alpha was 0.01. P is lower than alpha. P is less than alpha. When p is low, we reject the HO. Since we reject it, that means there is sufficient evidence to support the claim. That, what was our claim? Our claim was that older men have a lower mean weight than younger men. Remember, the average, the mu from older men is less than the younger. That older men have lower mean weight. Okay. Another example here. A study of zinc-deficient mothers was conducted to determine whether zinc supplementation during pregnancy results in babies with increased weights at birth. So the birth weight of a baby is something that's very important. We want babies to have a higher birth weight than a lower birth weight. If they are really, really small, that can be concerning. So generally, the doctors want the babies to have a little bit higher birth weight. Is there sufficient evidence that alpha equals 0.05? I'll go ahead and fill that in. To support the claim that zinc supplementation does result in increased birth weight. Okay, notice they've already given me the data, the n's, the x's, and the standard deviations for my zinc and the placebo. Placebo is like a sugar pill. It would be a pill that did not have the medication in it. So they gave some women the zinc supplement, and they gave some women a placebo, so that they didn't know whether they were getting the real zinc or just the fake drug that's just like a little sugar pill, because they really want to see if the zinc works or if it's just the idea to the women that they're getting something for their baby that was enough, okay? So they want us to see, I'm going to pick my zinc group to be group 1 and my placebo to be group 2. They want us to see if this zinc supplement, if the mean for my group 1 does result in increased birth weight, if those birth weight babies, or if those babies have a higher birth weight than group 2, okay? Remember, when we do independent samples here, mean from group 1 is equal to group 2. Our claim is that the group 1 will be higher than group 2. So I'm going to go to Stat, Test, 2 sample t-test, fill in my data. So X1 is 3214, standard deviation 669 out of 294 in my sample size. X2 is 3088, standard deviation 728, 286 in my sample size. My symbol was greater than, my symbol was greater than, leave it not pooled. It should give us our information. Our test statistic is 2.17. Our p-value is 0.015. We're going to compare p to alpha, 0.015 to 0.05. 0.01 is less than 0.05. Okay? Since p is low, we will reject the HO. That means there is sufficient evidence to support the claim that what? And what was our claim? Our claim was that the zinc supplement gave higher birth weights than the placebo. The zinc supplement helps in, I shouldn't say helps. Zinc supplement babies have higher birth weights. Because those babies weighed an average of 3,214 grams compared to 3,088 grams. Okay? So if you were the obstetrician for a pregnant woman, you might say, oh yeah, this zinc supplement is something I'm going to recommend to my patients because the patients who took this, their babies had a higher birth weight. Okay? And then the last example here, confidence intervals. So if you're doing a confidence interval for 2 mean samples, you pick 2 sample t int for your confidence interval. Okay? A randomized trial tested the effectiveness of diets on adults. Among 40 subjects using the Weight Watchers diet, the mean weight loss after 1 year was 3 pounds with a standard deviation of 4.9. Among 40 subjects using Atkins, the mean weight loss was 2.1 pounds with a standard deviation of 4.8. Construct a 95% confidence interval estimate of the difference between the population means. Remember, when they say difference, that's when we're looking to see if that 0 is in that interval. Okay? All right, so our 2 groups, we had Weight Watchers. I'm going to abbreviate that as WW. I'm going to let that be group 1. And Atkins was our other one. We'll let that be group 2. In both groups, we had 40 people, 40 subjects using Weight Watchers. So N1 is 40. Mean weight loss was 3 pounds. So X bar 1 is 3. Standard deviation, so standard deviation from group 1 was 4.9. 3 pounds does not seem like a lot of weight to lose, but anyway, all right. Atkins, 40 subjects, so N2 is 40. Weight loss was 2.1, so X bar for group 2 was 2.1. Standard deviation was 4.8. So we want a 95% confidence interval, and we're going to be comparing the means of the 2 groups at 95% confidence level. Remember, we will pick 2 sample t int. So stat, test, 2 samp t int, which is option O, 2 samp t int. And we feed in our data. We don't have the data, we have the stats. So the average for group 1 was 3, standard deviation 4.9, sample size was 40. For group 2, the average was 2.1, standard deviation 4.8, sample size was 40. Confidence level was 0.95. Again, we'll leave it pooled, we'll say no, and we will calculate. Our confidence interval was negative 1.259 up to 3.0592. Okay? So notice that interval goes from negative to positive. which means it does contain 0. Since it contains 0, that means the difference between the two weight loss groups could be 0. Well, if there's no difference, then that means, that you lose the same weight with either group. Okay? So there is no significant difference between the two groups, or between the two programs. Now, if I look at this and I go, I lost 3 pounds on Weight Watchers or 2.1 on Atkins, those are both pretty crappy. Neither one was a great diet. Okay, I didn't lose very much with either one. There was not a significant difference. But the real reason is not because I just don't think this is very much weight. The real reason is because their confidence interval contained the number 0. Okay, even if they had both been losing, 28 pounds here and 27 pounds here, if this confidence interval contained the 0, there would still not be much difference between them. In this case, there's no difference between them, and apparently they both stink, and they didn't lose very much weight. But even if they had lost a lot of weight, there's not much difference between them. It was about equal weight loss for each program. Okay?